All right, good morning, everyone. It's great to be back at GRCon. Great to see so many familiar faces. My name is Travis Collins. I'm a software manager at Analog Devices. My team focuses on transceiver-based systems, high-speed converter systems, as well as a lot of other components that ADI makes. If you're familiar with like the Pluto SDR, my team helps support products like that. Today, I'll be talking about some direct RF solutions that we have coming out. We'll have some corporate slides, but then we'll kind of get into some new interesting products that we have coming out. Now, if you're not familiar with Analog Devices, we're probably most known for our converter technology, our RF products, amplifiers, LNAs, mixers, and we've really grown our portfolio over the years through a number of acquisitions such as like Hittite technologies, where we've really grown our high-end RF space with linear technology, gaining more converters, as well as power products, and most recently with the Maxim Integrated acquisition to even push our portfolio even wider. And we're really providing full, we say like RF to bits solutions, and we're really a one-stop shop for that at ADI now. Right now we're a pretty large company, around 25,000 employees. We make 45,000 or more products, depending on how you count them, will determine what a SKU is or not. I feel usually sorry for the FAEs who have to deal with all these products and keep track of what they are. But it allows us to help you solve your most challenging problems and look at things from a true system level, where we can go from that front end, from your antenna, all the way back to your digitizers and getting data into your processing units. Now, I would say ADI does a few things really, really well. First of all, we integrate pretty heavily. So we'll take algorithms, we'll take new technology, new features, and put them inside ASICs that we design, so that you don't have to kind of implement things like IQ correction or automatic gain control, and we'll put those inside chips and allow kind of easier use and much simpler systems that you have, or more capable systems. And the second thing that we do really well is we really push the boundaries of technology. We're always pushing things to be more power efficient, faster, smaller, to make your systems much more capable. And this is really what I want to talk about kind of in the remaining of the presentation, is a product that is really pushing the boundaries of receiver and transmitter technology, and is going to be really disruptive in the marketplace. So if we just kind of start off first and talk about receiver technology over the years, typically we have three common architectures when we're looking at receivers. So in the top left here, we'll have a superhead design. And this is your real traditional radio, real high performance, but a superhead will require multiple mixing stages. So we'll have an IF that will bring a signal down to of interest, and then we'll bring that down again to baseband to do our final channel selection. And these systems are really high performance, but they typically require a lot of power and a lot of board space, because you just have so many discrete components. In the kind of the center bottom here, we remove a mixer stage, and we have what we call a zero IF or no IF receiver design. And a lot of the radios that you likely use today in your classroom or at work are likely this technology, because we're at a point where the performance is good enough, the power advantage is there, that just using this technology makes sense for a lot of the applications that you have. So the third one is kind of this new evolution or new frontier that we've been seeing and that we're enabling, I would say, now. I remember being a grad student and people were talking about direct RF or direct sampling and using radios of that architecture. And at this point, we are really here. We can do this, and we can go up to things like directly sampling X-band with our latest generation of converters. So with direct RF, you don't have any mixing stages. You directly sample from the antenna. You'll likely have some gain stages in there, but we're not mixing, we're doing everything digitally now. Now, this has a lot of advantages. The good thing is that it really decreases the complexity of your front end. You don't need multiple mixers. If you have a phase array system, typically with a superhead or a zero IF architecture, you would have to synchronize all of those front end pieces. When you remove them, we just need to make sure that the converters are synchronized. So you have fewer kind of components that are in your system. You can physically have a smaller PCB footprint because you're removing those components. Simpler to synchronize, and you get access to all this, like a large degree of instantaneous bandwidth now, since you can look simultaneously at, from DC to whatever frequency that you need to operate at. Now, unfortunately, this does come at a cost. One, you have to deal with that data. So when we're talking about like gigahertz or tens of gigahertz of bandwidth, you have to process that, and you have to be able to deal with that. And that's what we'll kind of focus on. Now, the second aspect you need to be aware of is that when you have direct RF systems or direct sampling systems, dynamic range is really important, because if you have, say, a strong interferer, that's really going to affect the sensitivity of your system. So you cannot, if you have a very strong signal somewhere in, say, like a low band, and you don't really care about that, you need to filter that out some way, or have a very high performance converter that can give you the dynamic range that you need to handle signals like that. So ADI has been building such converters, direct sampling converters, for almost a decade at this point. We started off with wideband DACs in 2014. We added on the ADCs soon after that. And more recently, we've been provided more integrated components. So in 2019, we introduced what we call an MXFE, or mixed signal front-end component. And this includes DACs and ADCs in one chip. And most recently, what we'll kind of spend most of the slides on is our latest generation called Apollo MXFE. And this is an ultra-wideband part that comes in two variants, a 4-transmit 4-receive and an 8-transmit 8-receive part, but at very, very wide bandwidths. So let's talk about Apollo. Apollo is, we don't typically release code names of parts, but this is kind of the exception to the rule here. The actual name of the part is Apollo MXFE. This is an extremely wideband part. It has 20 gigasample ADCs, 28 gigasample DACs inside. So there are 4 of those, 4 ADCs, 4 DACs inside the chip. And the laminate allows you to go up to around 18 gigahertz in actual RF bandwidth on the chip itself. So going beyond that, you'll just see further degradation of the signals that you have. But an extreme amount of bandwidth. So we're truly sampling X-band directly with this ASIC. So just to give you a little bit more detail, it's not just converters inside this part. So we do have, those really high-speed converters in the front of it, but on the right of this diagram, we can see there's lots and lots of digital that is inside the chip. So we're adding filters, decimation stages, NCOs. There's actually an FFT sniffer inside, so you can run an FFT at 20 gigahertz inside the chip. So you can, look at the front end and actually trigger pins on the outside of the chip if you need to react to signals that are coming in. But we're adding this DSP so you can deal with that 20 gigahertz, that 28 gigahertz of bandwidth that's moving in and out of the device. So pretty kind of extreme bandwidth that we're talking about here. Now, this kind of brings up a little bit of a conundrum. How do you really deal with a gigahertz or 20 gigahertz back in something like a new radio or any processing that you're doing? With even kind of standard transceiver-like devices that we have, where we're dealing with like tens or 20 or hundreds of megahertz, that is still challenging to do. Can we just hook up like 8 100 gig Ethernet connections to this thing and deal with that in GNU radio? You could try, but the chip is really not meant to be used like that. It's meant to be used with the DSP that's inside of it. So This is really what I want to kind of focus on here is how the chip is meant to be used, how these direct RF parts are designed, and how you would want to use that with something like a new radio. So I just here have it zoomed in on the one half of Apollo. So it's just kind of mirror the chip itself. We call it east and west sides. But on the top of the diagram is the DAC side. So we're coming in over GESD. We're going through different interpolation stages with NCOs, and then streaming out the DACs. And the receive side on the bottom is really just the same in reverse. So we'll have similar filtering capability. We'll have the FFT sniffer. We'll have decimation stages, and that will go to our SerDes lines over GESD back to our ASIC or processing unit or whatever you want to put on the back end. So now, if you kind of look at this in a traditional use case or use mode that a lot of our customers would take from our older generations of data converters, you would kind of like think of it like, well, I'll just take the converter and then route the data all back to my processing unit. I know how to program an FPGA. I know how to program a GPU or whatever. Let me just deal with that. And you're sucking in that full 20 gigahertz of bandwidth, which is, if you're used to doing multi-sample processing on an FPGA, 20 gigahertz is pretty extreme. So we would not really recommend using the part this way, but you can do that if you want that large bandwidth that's coming into the device. So really what you want to do is think of Apollo and the general MXFE family as a large channelizer. You want to use the decimation stages so we can pull out signals of interest and then just feed back the signals that we care about back to our processing units. So you don't want to suck back that 20 gigahertz. You want to enable as much decimation as you can, reduce the data rate, and just pull out the signals that you care about. Now, the nice thing about Apollo is that the internal decimations can all be uniquely configured. There are some rules around this, but you can independently set different channels. So if you want like a 20 megahertz channel, a 40 megahertz channel, a 60 megahertz channel, you can set up the part to do that all simultaneously. And you don't have to kind of have it completely fixed. You can actually change things so adaptively you can move and look and scan and then pull out the signal of interest that you want later on during runtime. So the chip is highly dynamic, is highly meant to be used in a way that adapts to your signal conditions for your environment. So, this is how you kind of need to think about these parts. It's not just a giant converter I need to deal with. It's a giant channelizer that I can use and selectively pull out the signals over that very large bandwidth that's coming into the converters. Now, to help with this, to help use the part directly, we've expanded out the configuration controls of the device. So here we just have kind of a system view where on the far left is the data converter, which might be on the same board or on an FMC card that you have. We'll have the FPGA in the middle, and then we'll have something like a new radio on the far right where we're doing our processing or we're doing our kind of control layers in the system. And the chip has been expanded to include more configuration control. So if you're familiar with like SPI, that will maybe go up at most like 100 megahertz. It has a similar interface that runs at 1.6 gig. That is a very high-speed control. So it's like really high-speed SPI. Think of it that way. There are 32 GPIO pins, so we can do lots and lots of dynamic changes that are deterministic, that map to over 120 functions on the chip. And finally, we have lots and lots of I/O. So if you really need to get that 20 gigahertz, or maybe a lot of different channels off the device, you have the capability to do that with the 24 SerDes lanes. So that's kind of a brief introduction to Apollo, the capabilities of it, and hopefully it gives you some understanding on these direct RF parts, how they're used, and how you need to think about them from a system level. They're not just a converter. You want to leverage the DSP and control them correctly in your system. Okay, so if you found this interesting, ADI is hiring. We have locations across the world. And if you're looking to learn more about Apollo, or other parts. If you have more questions, please come by the booth. We'd be happy to talk with you about it. Thank you very much.